everyone, and welcome back. My name is Mr. Koval, and in this video we're going to go over how to describe the bonding in certain molecules under valence bond theory. So let's get started. So in the first problem, we're asked to describe the bonding of HCN using a combination of hybrid atomic orbitals and unhybridized atomic orbitals. And we're told that the HCN molecule is linear. So the first thing we want to do is, from the information given, predict what the hybridization is going to be for your molecule. Since in this case we're told that it's linear, it's very likely that the molecule is going to have sp hybridization. So the carbon here is most likely going to be sp hybridized, and the nitrogen is going to be sp hybridized as well. And what that means is that you're taking an s orbital, an atomic orbital s, and a p orbital, one p orbital on the carbon, for example, combining those together so you get two hybrid orbitals. So you're taking two unhybridized atomic orbitals, you combine them, and you get out two hybridized hybrid orbitals. And so in this case, since you have a 1s and 1p, you're going to combine those, you get two sp hybridized orbitals. And so when we draw the structure, right, the carbon is going to have two sp hybridized orbitals, and the nitrogen is going to have two sp hybridized orbitals. So if we draw the carbon here, so carbon, and so we have an orbital there, so these are sp hybrid orbitals. And then we're going to have the nitrogen, and the nitrogen is also going to be sp hybridized, so this is sp. So there's two sp hybrid orbitals here, there's two sp hybrid orbitals there, and each of these hybrid orbitals are going to have one electron in each of them. So we'll have spin up, and then this one would be maybe spin up or spin down. We'll do spin down. This one will do spin up, and this one will do spin down. So there we're going to have a sigma bond here, because this is going to be the overlap of two hybrid orbitals, one from the nitrogen, one from the carbon. And so we have the combining of the two electrons, the single electrons from each of the atoms. That's going to form a bond there. We also have the hydrogen. The hydrogen is unhybridized, so that'll be here. So we got the hydrogen. This is the 1s orbital, and there's going to be an electron there. So here we have a sigma bond. So here we're going to have a sigma, and here we're going to have a sigma as well. And then in this here, we're going to have the lone pair. We're going to have a lone pair here for the nitrogen. And so that way we're setting this up for our sigma bonding structure as we did before. Okay, now that we've looked at the sigma bonding, we can look at how many electrons. Next thing we'll do is look at how many valence electrons are left over for each of the atoms. Hydrogen only has one valence electron, so that's already involved in bonding, so there's nothing left for hydrogen. But if you remember, carbon has four valence electrons, so we used one for the bonding here, and we used one for the bonding between for the hydrogen. And so that means we have two valence electrons left over from the carbon. And for the nitrogen, we have the lone pair here, that's two, and we have one valence electron here involved in bonding. This is not going to be involved in bonding since it's the lone pair. So nitrogen has 5 valence electrons. We use 3 of them here in our sigma bonding, right? Our hybrid orbitals, right? So then that leaves 2 electrons left over for nitrogen. So we have 2 electrons, 2 valence electrons left over for nitrogen, 2 valence electrons left over for carbon. Now, let's think about the unhybrid orbitals that we have left. This is sp hybridized. So if you remember, we take an S and we got 3 P's. So in sp hybridization, excuse me, we're taking an S and a P, and we're going to hybridize those, add those, combine those, and we'll get 2 equal energy sp hybrid orbitals, and then we're left with 2 p unhybridized p orbitals. So that means that we have 2 electrons left over for each of the atoms, nitrogen and carbon, and since they're both sp hybridized, that leaves 2 unhybridized p orbitals for both atoms. So that means we can put 1 electron into each of the unhybridized orbitals, the p orbitals, which means now those can actually form your pi bonds. So let's go ahead and draw our molecule so we can get ready for that pi bond structure. So we'll draw this again. We have hydrogen, and now we're going to draw lines to represent the sigma bond. So we'll have carbon, another line, nitrogen, we'll have our lone pair. So when we draw our orbitals, our unhybridized p orbitals, they're going to be perpendicular to the axis here. So we're going to have a z-axis, and we're going to have a y-axis coming out of the board into the board. So let me get my colors for that. Okay, so for the px, we could do px, py. So px is going to be up and down, perpendicular to the line here, and in the plane of the board. So I'm going to have my orange above. So this will represent something like the, positive wave function, if you will. And then I'll have blue on the bottom. Oh, let me make that bigger. That's 1. And then we have blue. Okay, so then that would be my px, right? So I have my px, and then if I do the py, it's going to come in and out of the board. I'll do my best to draw that. So here it's going to be looking like this. This will be like this. That's going into the board and then coming out of the board. It'll be more like this. Or actually, let me switch the colors around. Let me put the orange on the other side. I know it probably doesn't matter, but okay, so I'll put orange on this side. Okay. And then so this is coming out of the board. This is going into the board like so. And so each of these unhybridized p orbitals, so you got 1 unhybridized p orbital, then you have 1 unhybridized p orbital. So each of those are going to have an electron. So that'll be spin up, and we'll make this one spin up as well, like so. And then the other one, we'll put electrons in here. We'll make this spin down, and we'll make this one spin down as well. And so what's going to happen is that now if you have unhybridized p orbitals that have an electron and they are adjacent to another p orbital that has electrons, so we have two atoms, each has an unhybridized p orbital with one electron in them. The electrons are going to pair up, they're going to bond, and then you're going to get this overlap. So you're going to get this electron density overlapping like so. And you're going to get that here as well. And then you're going to get that on the other side with the blue. So here you're going to get overlap. And then here you're going to get overlap as well. Hopefully this is making sense. Hopefully you can see that. So then because you have two unhybridized p orbitals and they're overlapping with each other on between adjacent atoms, you get a pi bond for each one. So then your px is going to form a pi bond. And I forgot to label the py. So this is that's a py, and this is a py. So this is a py and this is a py. So these are going to overlap to form another pi bond. How do I want to? There, I'll do this. So we have a pi bond here and a pi bond there. So we have a pi bond that is in the plane of the board, perpendicular to the axis here. And then we have a pi bond that is coming in and out of the board, also perpendicular to the axis. And so you get two pi bonds, and you've got 1, 2 sigma bonds in the molecule. And so that's how you can describe what the bonding looks like and how to explain it. So what you're going to end up with overall between the carbon and the nitrogen is you've got one sigma bond, and then again between the carbon and the nitrogen you've got two pi bonds. So you got a triple bond between your nitrogen and your carbon. Here you've only got one sigma bond between the hydrogen and the carbon. Okay, let's go ahead and do our next example problem. Okay, so for our next problem, we're going to be looking at formaldehyde. So in this problem, it says describe the bonding in formaldehyde H2C double bond O, a trigonal planar molecule using a combination of hybrid atomic orbitals and unhybridized orbitals. I forgot a comma somewhere. Trigonal planar molecule. Okay, so just like before, the first thing we want to do is from the description predict what the hybridization is going to be. Since we're told it's a trigonal planar molecule, we should be thinking sp2 hybridized. So again, what that means is we got an S and we got our three p orbitals. We don't need the 3 there. And if it's sp2, meaning that you got one S and you got two P's combined together to form 3 sp2 hybridized orbitals that are equal energy, what that's going to look like is you've got the S and two P's, and these are going to be a little bit higher than the S but lower than the P, and that's going to leave one P left over. So we got sp2 hybridized plus a P. So we have one unhybridized p orbital left over. So we're going to have 3 sp2 hybridized orbitals on the carbon, and we're going to have sp2 hybridized orbitals on the oxygen. The reason for this is because oxygen here has a double bond. That's going to leave two lone pairs on the oxygen for an octet. So that's going to be three electron groups. So that's going to be three hybrid orbitals. So here, if we draw our picture, our hybrid, our sigma bonding framework is going to look something like this. So we have the carbon. We're going to have an sp hybrid orbital there, and then we're going to have an sp2, I should say, sp2 hybridized orbital, sp2 hybrid orbital. Now this carbon is going to have one electron. We'll call that spin. Oops. We'll give this spin down. We'll call this spin down. We'll call this spin up. Both of these are going to be bonded with or interacting with an unhybridized s orbital on the hydrogen, because we got two hydrogens here. So we're going to have an unhybridized s orbital for this hydrogen, and we'll have an unhybridized s orbital for this hydrogen. So we have that hydrogen there. So we got this single electrons paired up, forming a bond between carbon and hydrogen, and then here we have carbon overlapping with oxygen. So we're going to have oxygen here, and then that's going to have three sp2 hybridized orbitals on the oxygen. This one's going to have an unpaired electron, a single electron, and this is going to have the lone pairs. So we have spin up, spin down, spin up, spin down. So we have the two lone pairs on the oxygen. We have one single electron in this orbital that's going to pair up with the single electron in this orbital. So we have, again, this is sp2 hybrid orbitals. So we've got sigma bond here, sigma bond here, sigma bond there. And so here we have our sigma bonding structure. Now we need to figure out, well, how many electrons do we have left over? So for carbon, remember again, carbon has 4 valence electrons. We used 1, 2, and 3. So that means we have 1 electron left over. So 1 valence electron left over for the carbon. For oxygen, oxygen has 6 valence electrons. So we used 1, 2, 3, 4, 5. So that means we have 1 electron left over here. And because they're both sp2 hybridized, that means that we have 1 unhybridized p orbital left over on both the oxygen and the carbon. So both of those are going to be filled with 1 electron each. So let's go ahead and draw that. So we're going to redraw this so that this is perpendicular to the board. So we're going to turn this 90 degrees. And so when we draw this, it's going to look a little different. So we're going to have our carbon bonded to the oxygen. And then we'll have our 2 lone pairs, like so. And then the 2 hydrogens here are going to be perpendicular to the board. So when we draw that, I'll draw it the best I can. So three-dimensional structure like so. So there's my hydrogen going into the board, and then here's my hydrogen coming in out of the board. And so our unhybridized p orbital is going to be perpendicular to the plane. That's going to be our pz orbital. So again, I'm going to put the orange on top. So the orange lobe is going to go on top. And the blue lobe is going to go on the bottom. Let me make that bigger. Okay, and so then each of these is going to have one electron. So spin up, spin down. And so again, because we have an unhybridized p orbital on this atom, and adjacent to that we have another atom with an unhybridized p orbital, and they both have a single electron, that means that they can overlap, they can combine and form a pi bond. And so we'll get this overlap here. And excuse me, my voice. And we're going to get overlap here, like so. And so then we got our pi bond. So this is going to be our pi bond. So you could see that between the carbon and the oxygen, we have a 1 sigma bond, and we have 1 pi bond. So it's a double bond, which is shown here in our formula or structure, if you will. And so we have our lone pairs, and then we have the sigma bonds between the hydrogen and the carbons here. And so that is how you can describe the bonding for formaldehyde using both the combination of hybrid atomic orbitals and unhybridized orbitals as well. So I hope this was helpful. If this was helpful to you, if you enjoyed the video, then please by all means like the video, share the video, hit that like button somewhere over here. Also, make sure you subscribe to my channel. Do me a favor here. Also, when you do that, click on the notification bell and then click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have any problems or questions you need help with, or a topic you would like me to cover, put that down below. I would love to do that for you. Thanks for joining me, and have a great day.